Okay, so good morning to all. In the last class, we discussed some theory from group theory. So, some more theories we will discuss today. So, is Cayley's theorem. So, Cayley's theorem is very important thing. So, already we know that the symmetric group or the alternating group. Okay, what is that? Suppose if X is any set, any non-empty set, then A of S, A of X, A of X is nothing but set of all bijections. We are collecting function F. That function is a function from X to X is bijection function. We are collecting all bijective function from X to X. Then this set form a group with respect to the composition operation. That is A of X with respect to composition. So what do you mean by composition? There are two functions F and another function G in the set A of X. That is both F and G are bijection. Then the composition is defined to be F composition G of at a point X is nothing but F of G of X. So this is a composition of two functions. Okay. Now, with respect to this composition operation, this form a group. And this group is called a symmetric group. Okay. If it is X, if we take X is a finite set, then we become, we call it a permutation group. Otherwise, generally, if you take X is any set, maybe it's an infinite set also. Okay. So anyway, we can define A of X for any set. If X is finite set, suppose if X contains n elements, the coordinate of X is n, then this A of X is denoted by X suffix n, that is permutation group. Same thing, but we can use the different notation. S suffix n is a symmetric group, sometimes called or permutation group. Okay, now the Cayley's theorem says if you give any group is isomorphic a subgroup of A of X. Okay, that is a very important theorem. Cayley's theorem. Cayley's theorem. So all the named theorems are very important. So what the Cayley's theorem says, any group is isomorphic to a subgroup of a symmetric group. A subgroup of a symmetric group. So this is standard theorem. So if we take the special case, suppose if we take any finite group is isomorphic to a subgroup of Sn. Okay, maybe we can corollary of this Cayley's theorem. So this is general result. That means what? Given any group G, this is isomorphic to some subgroup H, but this is H is a subgroup of this A of X for some X. This is general result. Now the corollary says if you give any group of order n, if you give the specific order group, then it should be isomorphic a subgroup of Sn. Okay, that is corollary of this theorem. So what is any group of order n? Maybe it's a cyclic or abelian or anything, but any group of order n, any group G of order some n is isomorphic to a subgroup of the symmetric group Sn. So that is this G is isomorphic to a subgroup H, but this H is a subgroup of Sn. Okay, any group of order n is isomorphic a subgroup of Sn. Anyway, this subgroup also order n, but should be a subset of as a subgroup of Sn. Okay, therefore this Sn is very important because any group is isomorphic a subgroup of symmetric group, right? Therefore the symmetric group is very important. You should know all the properties of the group Sn. Okay, so this is very important theorem. Okay. Okay, now maybe I will give some theorems, very important theorems. So already we discussed what is cyclic group, what is abelian group. Now maybe I can write here some theorems, any cyclic group is abelian group. That is, cyclic group implies abelian group. All the cyclic groups are abelian groups. Why? So proof is simple. If we take some cyclic group, suppose if we take G is a cyclic group, therefore it is generated by some single element, maybe we call some A. Now we have to prove that this G is abelian. So that means what? If we take any two element x comma y, the commutative property is satisfied. Xy equal to yx. Okay, we take two element x comma y in the group G. But G is generated by single element A. Therefore, this x is of form a power some I, and y is power of a, that is a power some j. Now what is xy? If you consider the xy, x is nothing but a power I, y is nothing but a power j. Now the base is same, therefore you can add the powers, therefore a power I plus j. But I and j are integers, and we know that integers under plus is a abelian group, therefore a power we can write j plus I, because I and j are commutative property with respect to addition. Now we can split into a power j into a power I. But a power j is nothing but y, and a power I is nothing but x. Therefore, xy equal to yx for all x. We start with the arbitrary element x comma y is satisfy the commutative property. Therefore, G is abelian. Okay. So therefore, every cyclic group is abelian group. It's very important result. Now, the next result, but what about the converse? All the abelian groups are cyclic groups? No. There are so many, plenty of examples there. In general, abelian groups are need not be cyclic group. Abelian groups, that is xy equal to yx power l x satisfied, then the group need not be cyclic group. Abelian group need not be. Some abelian groups are cyclic, but in general, abelian groups are need not be a cyclic group. Okay, so maybe there are so many standard examples are there. Okay, maybe if you take the Q, maybe I can take the special group. So solution, what is that? If you take the group G is set of all rational numbers with respect to addition. Clearly, this is an abelian group because it's a group, and with respect to addition, x plus y equal to y plus x. If we take any two rational number x and y, the x plus y should be equal to y plus x. Therefore, it's a abelian group. But this Q under addition is not a cyclic group. Why is not a cyclic group? Okay, suppose Q comma plus is cyclic group, then what will happen? Okay, suppose Q under addition is cyclic group, then what will happen? So cyclic means what? The group is generated by a single element. That single elements come from the set. So that means what? There is an element from Q. But we know that every element of Q is of the form some m by n. So there exists an element m by n rational numbers in Q, such that Q is generated by that element m by n. Okay. Okay, that means what? If you take any element of Q, it should be a multiple of m by n. So that is the definition of a cyclic group. Because it's a group with respect to addition, if it is multiplication, there should be power of this element. But this group is a group with respect to addition. So therefore, if you take any element in Q, should be a integer multiple of this number m by n. Okay. So in particular, I am taking 1 by 3n because n is a natural number. Because since we take m by m, this n should be non-zero. Okay. So therefore, if you take 1 by 3n, this is also a rational number. Okay. Now, in particular, we know that we assume that this Q is a cyclic group. That means every element of Q is a integer multiple of some k times this m by n. In particular, if you take this element 1 by 3n, therefore 1 by 3n also should be a integer multiple of this m by n. Suppose some k times m by n. Now we can cancel this n because n is a non-zero number. We can cancel n. Therefore, the left hand side we get 1 by 3. The right hand side we get k times m. And we know that k is an integer and m, n both are integer. Therefore, m is also an integer. So k is an integer, m is an integer. The product is also integer. Therefore, the right hand side is an integer. but the right hand side is not integer. Therefore, which is a contradiction. Therefore, our assumption is wrong. So what is our assumption? We assume that suppose q with respect to addition is cyclic, we get contradiction. Therefore, this q under addition is not cyclic. It's a very important example. But Z is a cyclic group. Okay. So Z is a cyclic group, but Q is not a cyclic group with respect to addition. Okay. Therefore, Q with respect to addition is not cyclic group. So there are so many examples of abelian groups which are not cyclic group. So these are one of the example. So it is not a cyclic. So set of all rational numbers with respect to addition is not cyclic. Now there is some theorem. If you take any subgroup of a cyclic group is cyclic. If the given group is cyclic, then if you take any subgroup in that cyclic group, it's also cyclic. That is very important thing. So subgroup of a cyclic group is cyclic. Subgroup of a cyclic group is cyclic. Okay. So from this we can easily say that the R comma plus is not a cyclic group. Why R comma plus is not a cyclic group? Suppose R comma plus is a cyclic group, the subgroup also cyclic group, but Q comma plus is a subgroup. Okay, we know that. So therefore we know that the Q rational number with respect to addition is a subgroup of the real number R with respect to addition. Suppose this is cyclic group, then the subgroup also cyclic group because of this theorem. But we know that this is not a cyclic group. Therefore, this R comma plus is not cyclic. Okay. Therefore, if a small group is not cyclic, then if you take any bigger group, it's always not cyclic. Okay. So similarly, the complex number C with respect to addition, this is also not cyclic. Why? Suppose this C comma plus is a cyclic, then all the subgroups should be cyclic. In particular, this Q comma plus is also a subgroup of C comma plus, or you can take R comma plus also a subgroup of C comma plus. But we know that Q comma plus is not cyclic, therefore R comma plus is not cyclic. Therefore, C comma plus is also not cyclic. But in Q comma plus, it contains Z comma plus. But Z comma plus is always cyclic. It's generated by 1 and minus 1. This is cyclic group. But this is not cyclic group. This is not cyclic group. This is not cyclic group. Okay. So subgroup of a cyclic group is cyclic. This is also very important result. Okay. Now there is some characterization of any group of order prime is always cyclic. If you take any group, the order of the group is prime, then the group is automatically a cyclic group. Any group of order prime is cyclic group. So that is what I am saying. Suppose we have a group G, the order of the group is some prime number, either 2 or 3 or any prime number, implies that the G should be a cyclic group. Okay. It's a very simple proof. You have to use the Cayley's theorem, Lagrange's theorem. So how to prove this one? Suppose we have a cyclic, suppose we have a group of order P. Okay. So suppose we take some element, a non-zero element, because it contains P elements. Suppose I am taking some non-zero element, non-identity element A in the group G, where A is a non-identity element. Now, already we know that given any element in the group, we can form a subgroup. The subgroup is nothing but we are collecting all the powers of A that form a subgroup. So we call the subgroup is H. So this is nothing but the subgroup spanned by that single element A. So this is nothing but all the powers of A, that is A power n such that n in Z. Clearly this H is a subgroup of G. Okay, subgroup of G, because itself is a group and it's a subset of G, therefore it's a subgroup of G. Okay. Now, we know that by Lagrange theorem, order of any subgroup divides order of the group. But we know that the order of the group is prime number. Okay, so therefore, that number should be the order of P should be either 1 or P. So this is equal to P. Since this number is a divisor of P, and we know that P is a prime number, it has only two divisors, 1 and P. Therefore, the order of H either 1 or P. But the H is a cyclic group generated by A, but A is a non-identity element. Therefore, this H contains at least two elements, identity element and A. At least two elements H contains. Therefore, it cannot be equal to 1. Therefore, order of H should be equal to P. So, order of H should be the number P. And we know that the order of group is P, the subgroup also order P. Therefore, the H should be equal to the group, because the subgroup and the group have same order and it's finite. Therefore, the subgroup should be equal to the group G. But we know that this H is nothing but the subgroup generated by a single element A. Therefore, the G is also generated by a single element. Therefore, G is cyclic. Okay, therefore, any group of order prime is cyclic. What about the prime square? Any group of order prime square is abelian group, but we cannot say it's a cyclic group in general. Okay, so and then okay, I will come to the next one. Suppose if we have a two cyclic group A and B, then given any two groups, we can define the Cartesian product. Okay, so direct product or Cartesian product of two groups. So maybe I can say here. So direct product of groups. Suppose we have groups, then what is the direct product? So direct product of two groups. Suppose we have suppose I take n groups. So G1 with some operation star 1 is a one group, and we have another group G2 comma the operation is suppose star 2, and so on. We have another nth group Gn comma some star n. So we have n groups. Now we define the new group G is nothing but the Cartesian product of G1, G2, etc. Gn. We usually write G1 cross G2 cross etc. cross Gn. So this is nothing but how the elements look like. Everything is a n tuple. So G1 comma G2 etc. Gn, where the first element small g1 comes from the capital G1 etc. Therefore, this Gi belongs to capital Gi corresponding I, where I lies between 1 and n. Now this is a set. Now in this set we define the new operation star is nothing but term by term operation. So suppose if we take two element, suppose we take G1, G2, etc. Gn is a one element in G. Suppose if we take another element, suppose I check H1, H2, etc. Hn. So we take two element in the group G, but now the operation star is defined to be term by term multiplication, that is G1, G2, etc. Gn star, that is this star is new star. This operation for G, how we are going to define this operation is this is equal to G1 star 1, because G1 H1 is an element of the first group, but in the first group we know the operation is star 1. Therefore, the first coordinate is G1 star 1 comma H1. The second one is G2 star 2, because the operation is star 2 in the second group, and so on. The last group is Gn star n Hn. Okay, this is the operation. Now, with respect to this operation, this G form a group. This group is called a direct product of groups. Now, if you take what is the order of an element? So we know that in a single group, we know what is the order of an element A. So that is smallest n such that A power n equal to identity. Then we say n is the order of that element. Suppose if we take in the Cartesian product of the group, then what is the order of the n tuple? Suppose what is the order of the element G1, G2, etc. Gn. So we know what is the order of G1, what is the order of G2, etc. What is the order of Gn. Now what is the order of this one is the LCM of order of G1, comma, order of G2, etc. order of Gn. We have to take the order of, we have to find the order of each element and then take the LCM. That is the order of the n tuple G1, G2, etc. Gn. It's a very important result. Okay. So order of a tuple, maybe it's a n tuple or a two ordered pair. The order should be LCM of each order. Okay. Now we define what is the direct product of two groups, and this form a group with respect to the corresponding operations of the group. Suppose we have two cyclic group G1, G2. Suppose if we take the Cartesian product, is again it's a cyclic group. That is the question. The Cartesian product of a cyclic group, if we take two, and then we can extend it to any. So suppose what I'm saying, suppose we have two cyclic groups. What is the point? This okay, we can take 4, 5. Suppose G1, G2 are two cyclic group. Then or you can take A, B or G1, G2, any you can take. So G1 is a one cyclic group and G2, B, two cyclic groups, finite cyclic group. That is very important. This result only true for finite. That is both G1, G2 are finite cyclic group. So G1, G2 are two finite cyclic groups. Finite cyclic groups. Okay, if we take let, suppose we take two cyclic group G1, G2. Then the theorem says the Cartesian product G1 cross G2 is cyclic if and only if the GCD of the both order, that is GCD of the order of G1 comma the order of G2 should be 1. That is the order of G1 and the order of G2 should be relatively prime. That is the GCD should be 1. Then the group is cyclic. If the GCD is not equal to 1, the direct product of two cyclic group need not be cyclic. So sometimes they use the Cartesian product this cross, or sometimes they use this notation G1 the O plus direct product G2. Anyway, this is also a ordered pair of G element, and the intersection contains only the trivial element. So this is very important. Now another theorem is you know that given any order, we can always give a cyclic group of order that order. Suppose if we give any n, okay, for any natural number, for any n in n, this n is anything, 2000 or 3000 or 1 lakh or anything, we can produce a cyclic group of this order. So then we can have at least one. Then this Zn, integer modulo n, is a cyclic group. So we have any order, we have always a cyclic group. For any natural number, we have a cyclic group, namely Zn. And already we know the theorem, if we take any finite cyclic group of order n, then that group should be isomorphic to Gn, Zn. Okay. So any group is isomorphic, any cyclic group of order n is isomorphic to Zn. Therefore, we have up to only one cyclic group, only one finite cyclic group, namely Zn of order n. If we take any other cyclic, suppose we give any cyclic group, suppose G is any cyclic group. If G is any cyclic group of order m, then actually we can view this G is nothing but is isomorphic to Zm. Okay, Zm. So therefore, up to only one finite cyclic group of order m, namely Zm. If you take any other cyclic group, should be isomorphic to Zm. Okay, if you don't know about this group, don't bother about this, because these two are isomorphic. We know all the properties of these. Therefore, The same because it's isomorphism. So isomorphism part is preserve all the properties. If it is G cyclic, then ZM is cyclic. If ZM is abelian, then G is abelian. Suppose G contains of order 3 elements, then the ZM also contains the element of order 3. Therefore, isomorphism means what? Both are same, almost same. But maybe the structure is different, but the properties are almost same. That is isomorphic. Okay. So this theorem is very important. If you any cyclic group of order m, that group is nothing but Zn. Okay. So we have only one finite cyclic group of order n. Everything is isomorphic to this one. Similarly, if you take any infinite cyclic group, that should be isomorphic to the integers. So therefore, there are two important cyclic group. One is the Zn, another one is integers. These two cyclic groups are very important, because if we take any cyclic group, it should be isomorphic to one of these two. Okay, so in the cyclic group part, these are all very important points. So any cyclic group of order n is isomorphic to Zn. Any infinite cyclic group is isomorphic to Z. So I am sorry. Any infinite cyclic group G, suppose if we take any infinite cyclic group G, is isomorphic to, this is nothing but Z. Is isomorphic to the integer set of all integers Z. Okay. So that means what isomorphism is preserve all the property. We know about Z. Z is a cyclic group, Z is a abelian group, and Z have only two generators, 1 and -1, and all other only 0 have a finite order, all other elements have infinite order. So we know all about this Z. Therefore, we can easily say the properties of G if it is a cyclic group. Okay, that's a very powerful result, powerful of the isomorphic. Okay. So from this theorem, using this theorem, we can easily say a group is cyclic group or not. Okay. Suppose I am asking the question, what about the, suppose I am taking a real number with a non-zero real number. Okay. So exercise, suppose I am taking here. So is question. So is the R star. R star means nothing but we have to remove the 0 from real number. Then this form a group with respect to multiplication. Because one is identity element. If you take any two real number, non-zero real number, the product is also a non-zero real number. All the properties satisfied. Okay, this is a cyclic group or not? It is group, but we have to check it's a cyclic group or not. Suppose cyclic, then what you know? But what is the cardinality of this R star? R star is an uncountable set. Therefore, in particular, it's an infinite set. Suppose this is cyclic group, and is an infinite set, therefore is automatically isomorphic to Z, right? Suppose the group is cyclic, R star comma dot is cyclic, then the R star should be isomorphic to Z, because R star is an infinite set, and here we assume that is cyclic. Therefore, any infinite cyclic group is isomorphic to Z. Therefore, this R star is isomorphic to Z. So isomorphism means what? Is preserve all the properties, and we know that the Z contains only the finite order element, namely 0. So order of 0 is 1. And if you take any other element whose order is infinite, so only the finite order element is identity element in Z. But if we take here, so what about here? The multiplication is the operation, but here Z is a plus is operation. Therefore, don't bother about the structure. Okay. So now look at this -1. So -1 square is 1. Therefore, order of -1 should be 2. Because the power of -1 is 2, is 1. Therefore, order of the element -1 is 2. Therefore, this R star contains an element whose order is 2. But Z does not contain any element whose order is 2. Okay. So isomorphism will preserve all the properties. If suppose R star contains an element of order 2, then Z should contain an element of order 2. But Z does not contain an element of order 2. Because the Z contains only the finite order element is 0. All other element of order infinite. Therefore, this is not isomorphic. It's not isomorphic. Suppose R star is not isomorphic Z, then there you can easily say that R star is not cyclic group. So the seventh result is very important. We can easily say a group is cyclic group or not, and infinite group is cyclic or not. Using this theorem, we can check it. Okay, so it should be preserve the properties. Maximum you can take the order property. Similarly, for a finite cyclic group also, we can easily check. Okay, so this is very important results. So therefore, Cartesian product of two cyclic group is cyclic if and only if the order of both the groups should be relatively prime. Okay. Now the same thing. So now we compare the fifth point and then sixth point. Now we know that Zm is always cyclic group. If you take Zn and Zm, two cyclic group, then what is the Cartesian product when this is cyclic? So 8 point. So we know that Zn is always cyclic, any n. So I'm asking that Zn is a one cyclic group cross Zm is another number m is cyclic. If and only if. So when the Cartesian product of two cyclic groups cyclic, the order of each group should be isomorphic. GCD is 1. What is the order of the first group is n. What is the order of the second group is m. So therefore the GCD should be 1. So therefore Cartesian product of Zn cross Zm is cyclic if and only if GCD of m comma m should be 1. And already we know that order of any ordered pair, if you take any element here, so for example, if you take simple example, we can take how to find the order of an element in the group. Suppose if we take Z2 cross Z2. So Z2 is nothing but contains two elements. Z2 contains only two elements, 0 and 1. Now, how the element look like? 0, 0, and then 0, 1, and then 1, 0, and then 1, 1. Because this contains two elements, this contains two elements. Therefore, we know the formula for what is the order of the Cartesian product A cross B, where A and B are finite set. Then it's nothing but order of A, that is cardinality of A into cardinality of B. Now this is two elements, 2 into 2, 4 elements. Now we list all the 4 elements. Anyway, this group with respect to the point-wise coordinate addition. Now question is this cyclic or not? Is Z2 cross Z2 is a new group, is cyclic? No. No. Why? Because the GCD of 2, 2 is 2. Is not equal to 1. Okay, therefore, this is not a cyclic group. Okay, now what about the order of any element? So if we pick this element, this identity element, so always if you take any group, the order of the identity element is always 1. Okay, therefore in the group, so the order of the element 0, 0 is nothing but, so we can find the order of each element. So this is nothing but LCM of order of 0, the first 0, comma order of 0. But order of the identity element is 1, therefore LCM of 1, 1. So LCM of 1, 1 is nothing but 1. Now if you take the order of the second element 0, 1. So what is the order of this one? So that is LCM of order of 0, order of 1. So this is nothing but LCM of order of identity element is 1. What is the order of 1? So order of 1 is 2. Why? Because you can add 1 2 times. So if I just take only 1 times 1 is not 0, but if you take 1 plus 1 is 2. 2 is nothing but modulo 2. If you take modulo 2, 2 is nothing but 0. Therefore, if you add 1 2 times, you get 0. Therefore, order of 1 is 2. Because 0 is the identity element here. Therefore, what is the LCM? GCD is 1, therefore LCM is 2. Therefore, order of this element is 2. Again, you can see so that order of this element is also 2. Again, you can easily show that order of this element is 2. So, order of this element is 1. Now, we know that if G is cyclic, then there is at least one element in the group, the order of the group, and then order of the element should be equal. Okay, that is, I already said in the theorem. So, suppose order of the group is same as order of the element for some at least one element A, if and only if the group should be cyclic group. This is only for finite case. Okay, only finite case. So Suppose a group order same as order of at least one element, then the group should be cyclic group. Otherwise, this is not a cyclic group. Now we know that the order of the group is 4 because contain 4 elements. But this group does not contain any element whose order is 4. Maximum order is 2. Therefore, no element whose order is 4. Therefore, we can directly say that Z2 cross Z2 is not cyclic group because Z2 cross Z2 does not contain any element whose order is 4. Okay. So anyway, this is a method to find the order of any ordered pair. Now, if you take Z2 cross Z3, if you take the next example, Z2 cross Z3. This is cyclic. Actually, this is nothing but isomorphic to Z6 because, and this is one more result I can say. So if I go to and say that one, so that also very important result. Suppose if we take 6th, 8th, 9th point, if we take Zn cross Zm, this is isomorphic to the product Z suffix Nm. When this is happen, only when if and only if the GCD is 1. The GCD of n comma n is 1, then Zn cross Zm is nothing but Z suffix Mn. Okay, it's very important result. So only when the GCD should be 1, otherwise not true. So therefore, we can easily say that the Zn, Z2 cross Z3 is isomorphic to the product Z6. Therefore, this is cyclic group because here, so to check this is cyclic group or not, it is enough to check this cyclic group or not because both are isomorphic. And we know that Z6 is always cyclic group. I already mentioned that Zn where any n is cyclic, therefore Z2 cross Z2 is cyclic group, and then we know how to find the order of everything. Okay. So therefore, this is very important point. Okay, maybe I will solve one problems related to this. And then the symmetry groups are also very important. Now we will discuss some example. It is asked in the JAM exam. Okay, now the first question is, yeah, we know about S3. S3 is nothing but symmetry group on 3 symbol or permutation groups. Okay, suppose I am considering the direct product of the two groups. Sometimes I am using this, use the notation. Okay, sorry, 3. S3 direct sum or direct product of S3. So this is nothing but everything is ordered pair. First pair comes from first element comes from S3, second element also comes from S3. Okay, so this is a group. So they use this notation. This is nothing but S3 cross S3. Okay, both are same, but they use this notation. Sometimes they use this notation, but better use anything you should know. Okay. Now, what is the question is, what is the maximum order in that group? Okay, so question is, so this is a group G. Okay, the direct has an element of order. So now I give the 4 option. So what is the possible? Suppose I take 4, and then the second option is 6, and the third option is 9, and then D, the last option is 18. Now, what is the group order actually? So here, what is the group? G is nothing but the direct product. So G is nothing but S3, the symmetry group S3 cross S3. And we know that the cardinality of S3 is nothing but 3 factorial. So 3 factorial is nothing but 6. Now, therefore, what is the cardinality of G? 6 into 6, therefore 36. So the group order is 36. Now, how the elements look like in G should be ordered pair. So sigma comma tau. This is element, if you take any element in G is of the form sigma comma tau, where sigma is a one permutation, tau is another permutation. All possible combination. And we know that how to find the order of any ordered pair. So okay, so order of, take any ordered pair, sigma comma tau is nothing but LCM of order of sigma comma order of tau. Okay, now what is the maximum order? So first I recall what is S3. So already we know that S3 is a set of all bijection from the 3 element sets to 3 element sets. It contains the identity element, identity function, and then 1 maps to 2, 2 maps to 1, and 3 is maps to 3. And 1, 3 means what? 1 maps to 3, 3 maps to 1, 2 maps to 2. And that one is 2, 3. That is 2 maps to 3, 3 maps to 1, 1 maps to 1. And then next one is 1 maps to 2, 2 maps to 3, 3 maps to 1. Cycle notation. And then 1 maps to 3, 3 maps to 2, 2 maps to 1. So there are 6 elements. Now already we know that what is the order of a permutation cycle is nothing but length of the cycle is called the order. Now look at this. The order of identity element is always 1. What is the length? The length is 2, therefore order is 2. The length of this permutation also 2, therefore order is 2. And then length is this is 2, and the length is this is 3, and this is length 3. Therefore, if you take any element in S3, the orders are either 1 or 2 or 3. There is no order, no, there is no element of order 4, there is no element of order 5, there is no element of order 6. Now, if we look and consider the G, S3 direct product S3, that means every element is of the form the ordered pair. Now, what is the question is the S3 direct sum S3 as an element of order dash. That means what is the maximum possible? Because it's nothing but LCM. So the order of we know that order of any permutation is nothing but LCM of order of sigma, order of tau. But order of sigma possibles are either 1, 2, 3. Again, the order of tau also the possibles are 1, 2, 3. So for what combinations will get a more value? You understand my question? So this is the only possible order in S3. Then what is the order of S3 cross S3? So what is the LCM? You can take LCM of these two is 6. What is the LCM of these two? 3. What is the LCM of these two? 2. Now we get the maximum is 3, sorry, 6. Therefore 6 is the 6. We have an element of order 6, namely the permutation. In the first group, I take the element. Either you can take 2, 3 or 1, 2, 1, 3 or 2. Anyway, I take the first permutation should be order 2 element permutation. The second I can take order 3. Or first you can take order 3 or order 2. Anyway, the maximum order is 6. So therefore, this composition S3 direct sum S3 has an element of order 6. There is no element of order 9. If you suppose there is an element of 9 means what? The LCM should be LCM of some two numbers should be 9. So what is the possible that when we get a LCM is 9? Only when the first one is 1 or 9. So the LCM of 1, 9 is 9. That is the only possible. If you take LCM of 3, 3, you get 3, not 9. So we get 9, the LCM of two numbers, namely 1 and 9. But anyway, the permutation contains the order 1, namely identity element. But the permutation does not contains any element of order 9 because the maximum order is 3 in S3. Therefore, it does not contain any element of order 9. Therefore, we cannot get 9 as an LCM of elements of this one. So therefore, 9 is not wrong answer. 9 is wrong, therefore 18 also wrong. So when we get a 18 as a LCM, so we can take what is the possible? Is that 9, 2. The LCM of 9, 2 is 18. But anyway, the group contains the element of order 2. But so when we get a LCM is 18, the possible is 2, 9. Because GCD is 1, therefore the product is the LCM. Therefore, we get a 18 as a LCM only when either 2, 9 or 9, 2. So anyway, the permutation contains an element of order 2. Namely, either you can take 1, 2 permutation or 1, 3 permutation or 2, 3 permutation. But the S3 does not contain an element of order 9 because the maximum order is 3. Therefore, 18 is not an answer. Now again, if you take 4, what is the, when we take, so when we get a LCM is 4, the only when we have 4, 2. Because the GCD is 2, therefore LCM is 4. So this is the only case, or 2, 4. Now, anyway, the permutation contains an element of order 2, but it does not contain the element of order 4. because the maximum order is 3. Therefore, we cannot get an element whose order is 4 in S3 cross S3. The only possible is 6. And even you can say 6 is the maximum order of an element in the group S3 cross S3. What is the maximum order in S3 is 3. If we take the Cartesian product S3 comma S3, the maximum order is 6. Okay, so this is very important. This is a question asked in the JAM examination. Now maybe I will one more question I will state here. So if you have any doubt, you can ask. So the next one is, this also asked in the same exam. Which of the following are true? Are true, that means more than one options may be true. So which of the followings are okay, is are, so both the conditions followings is or are true. So the first option is Z3 direct sum Z3 is isomorphic to Z9. Second option, Z3 direct sum Z3 is isomorphic to Z6. The third option, Z4 cross Z6 is isomorphic to Z24. And then the last option, Z2 cross Z3 direct sum Z5 is isomorphic to Z30. Now, what are the correct answer? So please tell me in the chat box, type in the chat box which one is correct. We know the theorem. So anyone know the answer? Use the previous result. So we know that when the Cartesian product Zn cross Zm is isomorphic to Z, the product of two numbers, we know that. So what is the correct answer? Anyone? Okay. So since look at the first option, Z3 cross Z3 is isomorphic to Z9. No. So when this is happen, only when the GCD of 3 comma 3 is 1, then it is true. If GCD of 3 comma 3 is 1, then this isomorphic is the product. But what is the GCD of 3 comma 3 is 3, not equal to 1. Therefore, this is false. And here, look at the second option. What is the order of this? Is nothing but 3 into 3. The order is 9 here. So the number of elements on the left hand side is 9. But here, Z6 order is 6. Number of elements in Z6 is 6. Therefore, it cannot be isomorphic. Isomorphic means that both the order should be equal. Okay. Therefore, the second one is wrong. Now look at the third one. Z4 cross Z6. And we know that GCD of 4 comma 6. What is the GCD of 4 comma 6? Is 2. Is not equal to 1. Therefore, is not isomorphic the product. When this isomorphic to the product of the number, only when the GCD should be 1. But GCD of 4 comma 6 is 2. Therefore, this is not isomorphic this. Now look at the last option. If you take the GCD of these is 1, or you can take the GCD of these two is again 1, or you can take the GCD of these two is again 1. Therefore, it's nothing but product of the numbers. So the product is 6 into 5 is 30. Therefore, this is the correct one. So I stated previously only for 2 cases. We can extend in the n case. That means what? Suppose we set n. So Zm1 is a 1 number cross Zm2 cross and so on. Some some number L is isomorphic to Z, the product of all the numbers M1, M2, etc. ML. So when this happen, only when if you take any two number, the GCD should be 1. That is, if you take any two number Mi, Mj should be 1, but I not equal to J. If you take the different numbers, the GCD is always 1. Then the Cartesian product is isomorphic to the product of the number Z suffix M. So if you take here M1 is 2, M2 is 3, M3 is 5. If you take any two numbers, the GCD is 1. If you take GCD of 3, 2 is 1, 2, 5 GCD is also 1, 3, 5 is GCD also 1. Therefore, isomorphic the product. Therefore, the last one is the correct answer. Okay, so these are all very important things. Okay, now we discuss some other problem. Okay, there are some. Okay, in algebra we have so many theorems you should remember. Okay, so there is some concept of isomorphic, number of isomorphic, non-isomorphic. Okay, the next important theorem, a fundamental theorem of finite abelian group theorem. Okay, that is finite abelian group theorem. It's very important theorem. What is the theorem says? If you take any finite abelian group, its isomorphic to, we can write as a direct product of cyclic groups. Okay, any finite abelian group is isomorphic to, or it's is equal to or isomorphic to direct product of cyclic groups. Direct product of cyclic groups. It's very important result. It's only true for only finite abelian group. Any finite abelian group is isomorphic to direct product of cyclic groups. Since G is finite abelian, therefore the cyclic groups also finite cyclic groups. Okay, so maybe I read some example. So how to find the cyclic groups and then how to write this one. For example, suppose G is a finite abelian group. Suppose we take some order. Suppose of order, if you take some number, what is the number I can take? Suppose I am taking 15. So G is a finite abelian group of order 15. Now, how to write this G is a direct product of cyclic groups. So one way is, first we have to factor this 5 into product of prime powers. So 15 can be written as 3 into 5, just two numbers. Therefore, we can write this G is isomorphic to Z3 cross Z5. This is one way. And then otherwise you can write just isomorphic to Z15. But anyway, both are equal. Why both are equal? Since the GCD of 3, 5 is 1, therefore this is isomorphic to the product Z15. Therefore, we have only one non-isomorphic abelian groups, namely Z15. We have only one. The number of non-isomorphic abelian groups of order 15 is only one. Okay. We can write only this is only the only form is this one or this one. Anyway, both are this isomorphic. And this is number of isomorphic. Okay, we have only one non-isomorphic, because if we take, there are two. So order 15, we have two cyclic groups only. Namely, Z3 plus Z5 is a one cyclic group of order 15. Another one is Z15. Okay, there are two cyclic groups, but these two are isomorphic. Why? Because the GCD of 3, 5 is 1. Therefore, this is nothing but isomorphic, the product. Therefore, we have only one non-isomorphic. These are isomorphic, these are all isomorphic. So we take only one in the collection. Okay. Suppose the question asked in the JAM examination. Suppose G is a group of order 17. So okay, exercise. So the problem is, let G be the group. Let G be a group of order 17. Of order 17. Then the total number of non-isomorphic groups. Non-isomorphic. Actually, they asking, sorry, subgroups. They asking how many subgroups are there. Subgroups of G. So since this 17 is a prime number, therefore there is no proper subgroup except the identity element. Therefore, the only subgroups are H equal to singleton E is a one subgroup, another is the whole group. So only two subgroups because the group order is prime number. Okay. So we have two subgroups because any group is a subgroup to itself. Therefore, G is also a subgroup. The singleton E is also a subgroup. Therefore, these two subgroups are not isomorphic. Why is these two are not isomorphic? Because the order of H is 1 because contain only one element, and then the order of G contains 7 elements. Therefore, these two subgroups are not isomorphic. Therefore, we have one non-isomorphic subgroup, another non-isomorphic subgroup. Therefore, there are two non-isomorphic subgroups. Okay, the answer is 2. Okay, so there are some results are there. Maybe we will discuss later. Now I stop the recording. Thank you.